Uh, it's my pleasure to welcome you to the session here, to this year's edition of the SRC, stands for the Student Research Competition. We have six fabulous students. Thank you, Ohad, for the 5 minutes. We have six fabulous students this year giving talks and a poster session afterwards at the reception. So we'll start with the talks here. There'll be 5-minute talks, sort of lightning talks, introductions to the research area. There will be no Q&A. The Q&A will be afterwards during the reception. There will be an extended 1.5-hour Q&A, I believe. So please ask your questions then. And do please make sure to visit the posters when you're out there and talk to the students. And I think, I don't want to keep talking, I think we should just get started here. And the first one will be Kai from the University of Oxford. If you come up here, yes, thank you. To tell us about, what is it, higher order hardware description, semantics of synthesis time computation.
Okay, thank you everyone. Yeah, I'm Kai. I'm talking about, higher order hardware description. So I'm going to start with just a simple example. So this is kind of a silly little circuit that adds 3 bits together, full adder. And we have a let expression here that defines a half adder, which is like a subcircuit of this circuit. And we can see that we use this subcircuit 2 times, but we only have to define it once. So this is kind of an example of like trying to make our hardware programs more concise, right? And this is something that we actually do in real hardware description languages all the time. In Verilog, we have modules, and we can reuse modules and kind of use them many times. And we have other features in Verilog as well. We can use kind of synthesis time loops and elaboration time constants. And there's quite a lot of computation that happens in between us writing the hardware description and actually synthesizing it into something that goes onto an FPGA or ASIC. So I'm interested in kind of this type of thing. And then there are other languages like Clash that are particularly exciting because we have the whole power of Haskell. We have kind of higher order functions and all these different things that we can do before we even get to the synthesized hardware. So this is kind of the process that I'm interested in. And I'm particularly wondering, how do we look at the semantics of a language that features kind of synthesis time computation as well as a description of hardware? So I'm going to look at just a very simple setting that features kind of combinational circuits as well as the simply typed lambda calculus. And that's going to let us kind of define some functions between circuits and higher order functions so that we can look at this type of thing, right? So this is just a very silly little kind of example of the same half adder thing, but written as a function. So we take an implementation of the half adder as an input, and then we use it twice, and then we get a full adder as output. And then we can kind of reduce this function and get the desired hardware that we have. So more formally, we define like this syntax that kind of splits circuits into the hardware component, which consists of kind of these wires that are either pairs or projections or applications of functions, as well as kind of circuits that feature this lambda calculus that lets us do synthesis time computations. And what I'm interested in is how do we look at this semantically and make sure that it's sound in the sense that like when we look at the meaning of one program and then we evaluate it, we get the kind of intended meaning that we were aiming for. So in particular, when I'm talking about the semantics of hardware, we really mean the semantics of the physical hardware. So we want to distinguish between 2 equivalent circuits that maybe have different numbers of gates. So we want to distinguish between copying and sharing circuitry. And this is a very interesting distinction because it comes up in other settings as well. So probabilistic programming has the exact same distinction because it's also kind of a commutative effect. And so it has the same type of thing where if we generate a random number and then use it twice, that's very different from generating 2 different random numbers. And so this kind of connection between these 2 areas is very interesting from a semantic point of view because we can use a lot of the kind of existing semantics for probabilistic programming for hardware because it has a very similar structure. So I use Markov categories as a semantic interpretation for wires, and I use nominal sets as a semantic interpretation for circuits because circuits kind of contain this lambda calculus, and so they need to have a Cartesian closed category. And so this is kind of our semantic framework. And then through this, we kind of get some theorems. We have a normalization theorem that says if we type everything properly and there are no higher order types, then we end up with kind of the circuit that we wanted once we evaluate everything. We also have a soundness theorem that says that all along the way we kind of stay with the hardware that we intended. And then I also give a kind of implementation that shows that you can actually use this. So you can kind of write a little hardware description program in a slightly kind of extended version of this calculus with some syntactic sugar. And then type inference happens, and some various simplifications happen, and we do this kind of reduction, and we end up with a Verilog program that we can either like put on an FPGA or simulate, or turn into kind of actual hardware. So yeah, that's kind of my project. That's my research. Thank you very much for listening.
Thank you. All right, let's set up for the next speaker here. Who's next is Andrew. It's a bit like, you know, in the Formula One when they change the tires. All right.
Which one is it to forward? Great.
All right. Please welcome Andrew, and Andrew will tell us about serving FPGA technology.
Great. So am I good to start?
Yes.
Awesome. Hello, everyone. My name's Andrew. I'm a master's student at the University of Washington with the Pulse Group. And today I'm going to talk a bit about my research, assessing hardware compilers, and see how well they're taking advantage of the hardware that they're actually compiling to. So, as a quick refresher, hardware compilation works a lot like software compilation. Essentially, in this diagram here, you have some high-level design fragment that at some higher level of abstraction says what the hardware should do. You feed that into your favorite hardware compiler, which of course is Yosis, and as output, you get some low-level implementation in terms of smaller FPGA primitives. Now, these FPGA primitives, they can end up being quite complex. As here you can see on the diagram, this is the DSP-48E2. It's a digital signal processor that's on the Xilinx UltraScale Plus FPGA architecture. It's quite complicated, and it implements very many things, but some of those things are this expression you see up on this slide here, which is 4 data inputs that have these sort of logical or arithmetic operators flowing through them. Now, one thing to note is that this complexity makes FPGA primitives very powerful. With just one of these complicated primitives, you can efficiently implement like several microdesigns. But this complexity and this power is really super useful to the end user if and only if hardware compilers are actually fully utilizing them. So I guess a natural question from this is, what does that actually look like? Well, let's go through an example of what that doesn't look like. So I'm a hardware designer, that's me, and I have a design that I know will go onto exactly one of these specialized DSP units. After reading the documentation, I've come to this conclusion. So I write up one of these micro designs, and I feed that as input into one of my favorite hardware compilers, which is one of these. And then as output, I get something that isn't just a DSP, but instead it's multiple of these primitives. It's not just one DSP, but there's this extra one added to the side, and then I also have this extra lookup table. These extra primitives, I know after reading the documentation, are unnecessary. I could have just used one of these primitives to efficiently implement the design, but instead I've got these extra ones that end up making the design overall less performant, and they give it a higher area. So the end result is that I'm a very, very grumpy hardware designer. Now, is this something that actually happens? Is another natural question, and the answer to that is yes. All it takes is a simple Google search to go to your favorite hardware forum to see posts just like the 3 that I've screenshot here that are sort of saying that they're complaining about this exact case. I have a design that should go onto a specialized primitive, but instead it's going onto many. Now, from these forum posts, we can infer that the support for these primitives is incomplete. But the question is, how incomplete are these primitives? Existing work has been done that rigorously evaluates these hardware primitives on dimensions of correctness and also dimensions of performance, but no such work exists to evaluate these compilers on how well they're taking advantage of the power of the individual primitives. So to answer that question, I built what I like to call Cookie. It's a tool that evaluates hardware compiler completeness by quickly enumerating over a design space. Now, the flow for Cookie ends up being relatively straightforward. We start with some suite of initial designs that we know should go onto exactly one specialized primitive. We then tweak each one of those designs on several dimensions, including, say, the signedness of the inputs or the number of pipeline stages. This quickly helps us enumerate and build a test portfolio that we can then plug into several hardware compilers. From there, it ends up being sort of case by case. Either we have the case where the compiler succeeds and we get a single primitive implementation that's efficient, or we get the interesting case, or we get that the hardware compiler has sort of this completeness error, and we get an inefficient multi-primitive implementation. And part of my research has discovered that across every compiler that we've seen so far, or that I've seen so far, there are sort of these completeness holes. So thank you very much for listening, and I'd be happy to chat more about this with you later. Thank you.
All right, next up is Cynthia. And Cynthia is going to tell us about what is a good rule set. Please take it away.
Hi, so I'm Thea, and this is my talk on quality saturation and how we can figure out if something is a good rule set. So this is a talk about equality saturation, which maybe you've heard of, but I'm going to assume you haven't. So equality saturation is a technique that uses a data structure called an E-graph to perform non-destructive term rewriting, which means that we never lose information. And equality saturation is used in real applications. These are the ones that have logos, which depend on rewrite rules to determine equivalence. And this is like an example of a rewrite rule right here. So if we have an application, we might at some point want to compare one rule set to another to see which is more complete or useful, but that's kind of hard. Certainly it's hard to do just by looking, or maybe we don't have the benchmarks, or the benchmarks take a long time to run. Also, we don't want to just throw every rule we can think of into our application, because too many rules that aren't useful will add lots of information to the E-graph, leading to performance issues. So to combat this, we use this notion of derivability. And we say that a rule is derivable by a rule set if its left and right-hand sides are determined to be equivalent following the application of rules in the other rule set. But that's a little vague. So more concretely, we've come up with variants of derivability. Say we want to see if we can derive the rule x rewrites to y using y rewrites to x. One choice that we might make is initializing the E-graph with just the left-hand side of the expression. Or we could choose to initialize it with both sides of the expression. And what we see is that different variants of derivability actually result in different behavior. So here, the rule y rewrites to x fires and merges x and y in the E-graph. So we report this rule as derivable. But on the left-hand side here, we actually see that no rule fires, and so we can never report that rule derivable. We also find that there are performance differences in terms of derivability. So in this case, we have the rule x rewrites to z, and the rule set containing these three rules. And here we do the same thing. We initialize one side with just the left-hand side, and the other side with both sides. And what we see is that when we initialize with the left-hand side only, we need to take 2 steps, whereas on the right, we only have to take 1 step. And this is like a very simple example. Like in this case, we probably wouldn't run into performance issues, but in practice, you can imagine a rule set where there is a theoretically derivable rule, but it takes a lot of steps. And in practice, equality saturation tends to blow up within a relatively small number of iterations. And so we may enter a situation where something should be derivable in theory, but in practice, timeout occurs before we can derive it. So now the question becomes, why would we pick one approach over the other? Well, we want to think about how the rules are going to be used. Some equality saturation applications, like Herbie, which is this little car, are optimizing applications. Herbie is used for optimizing floating point expressions. But other applications, like the Certora verifier on the right here, are equivalence checking, meaning that they are trying to determine if 2 things can be said to be equivalent. And if you think about it, one of these is a lot more like the version of derivability that uses just the left-hand side. That's the optimizing side. Because we want to take something, apply some rewrites to it, and then see what we end up with. But in equivalence checking, we have a goal in mind, and we want to see if we can get there from a starting point. And so in that case, we might want to initialize the egraph with both sides of the expression. And yeah, that's it. We have an abstract here if you would like to read it. Thank you.
Up next, we have Ernest.
Which one's forward?
All right, you ready? All right, so welcome Ernest here. He's going to tell us about Mica. Yeah, take it away.
Hello, I'm excited to talk to you today about Mica, which is a tool that automates differential testing for the OCaml module system. In the ML module system, we can have representation independence. This means I can have two modules, M1 and M2, that implement the same interface I, but M1 and M2 might implement I in completely different ways. We sometimes also call I a module signature. Here's a concrete example. Suppose I have an interface for finite sets. I have an abstract type, alpha t. I have the empty set. I can add to a set. I can take the union of two sets, and so on. One way I can implement sets is naively using lists. Here, of course, I have to maintain the invariant that the underlying list can't contain any duplicates. Another way I can implement sets is by using binary search trees. Here, I have to maintain the canonical BST invariants. Now, a natural question arises. Are my two implementations equivalent? Morally, does my union operation on lists behave equivalently to my union operation on BSTs? Specifically, the notion of equivalence we care about is observational equivalence, which informally says given equivalent inputs, do the functions in my two modules produce equivalent outputs? But how do we test for observational equivalence? Well, one way of doing so is by using property-based testing. This is a manner of testing in which we first write a property, an executable specification describing some desirable behavior of my program. I then write a generator, a function that produces random inputs with the desired type and shape. And then I check, do these random inputs satisfy my property? Property-based testing was popularized by the celebrated library QuickCheck in Haskell. Now, here comes a problem. Writing property-based testing code for different modules requires significant programmer effort. This is because my abstract type is instantiated differently across my two modules. Mica is a tool that aims to solve this problem automatically. This is how Mica works. As the user, I give Mica a module signature and two modules implementing the same signature. Mica parses this signature and automatically generates property-based testing code specialized to this signature without any programmer interference needed. Now, I promise that all of the code I'm going to show you from now on is automatically generated by Mica. The first thing that Mica gives us is a data type, an algebraic data type of symbolic expressions. For each declaration in my original module signature, we produce a constructor for this algebraic data type that shares the same name, the same arity, and the same argument types. You will observe that the empty variable in the signature corresponds to the empty constructor, the add function corresponds to the add constructor, and so on. Mica also gives us these two auxiliary algebraic data types that represent the types and values of my symbolic expressions. Mica also automatically produces the definition of a QuickCheck generator for random well-typed symbolic expressions. This generator, genexpr, takes in an argument which represents the type of a symbolic expression. genexpr t promises to only give us random well-typed symbolic expressions of type t. Here's an example of a well-typed symbolic expression. This is well-typed because I can take the intersection of two sets. This, however, is not well-typed. SizeEmpty gives us an int, but isEmpty expects a set as its argument. And genexpr promises to never give us this bad symbolic expression. Mica also automatically gives us an interpreter for symbolic expressions. This interpreter takes in a symbolic expression and interprets it over my module implementation, producing a corresponding value. And Mica also gives us an executable for testing observational equivalence. Here we're using Jane Street's fantastic core quick check property-based testing library to do this. So how do these pieces fit together? Well, we first run our generator to generate random symbolic expressions. We interpret them over our two modules, and then we run our executable to test for observational equivalence. Here are some case studies of modules we've tested Mica with. We've tested Mica with 2 implementations of regular expression matching, 2 implementations of purely functional maps, 2 implementations of polynomials, and 2 implementations each for stacks and sets, respectively. If you remember nothing else from this talk, remember this. Checking observational equivalence for 2 ML modules requires significant programmer effort. But thanks to property-based testing, Mica can automate this process. Mica is here for you. Thank you very much. See you at the poster session.
Hello. Very quickly. Here's a tutorial. Please speak into the microphones, okay? Not like this. Not like this. Like this, okay? Otherwise, we will get feedback and we will get bad quality, okay? Thank you.
All right, we'll just move on. Vishal is the next.
Is this close enough? Is this close enough?
All right. Well, welcome Vishal to the stage, and Vishal is going to tell us about sketch-guided synthesis.
Yeah. Hi, everyone. I'm Vishal. I'm an undergraduate at the University of Washington. And I know there's been a lot of hardware talk so far, but we're going to do one more. We're going to talk about sketch-guided synthesis applied to FPGA compilation. So we're all PL people. Let's talk about hardware compilation just to get a little bit more context on it to know what we're talking about. In general, this talk, I'm just going to give some context on the background problem. That way, during the poster session, we'll have a better time talking about more interesting things. So what does FPGA compilation actually look like? Well, first, let's get an analogy into the software world. In software compilation, we start in a high-level language. Here we have everyone's favorite high-level language, C. And we pass this in through a software compiler. This is a program that we want to execute. When we pass it in through our favorite software compiler like GCC or LLVM, we get out a low-level representation, which is architecture-specific. In this case, I think it's x86. In x86, we have x86 instructions that can be performed by a computer. The hardware design world is not actually so different. In the hardware design world, we start off with a high-level design that we want to implement on our FPGA. This hardware design is then passed in through a hardware compiler, and this hardware compiler outputs a low-level design in terms of FPGA-specific primitives that can then implement the design. So what's different about this process other than the fact that the software compilers have cooler logos? For one, FPGA primitives are a little bit different than instructions in a few key ways. So FPGA primitives are the literal physical modules on an FPGA that can implement a design. There's many different types of them, and they all have a little bit of a different process when it comes to the hardware compiler. First, we'll start off with some simple primitives. So you may have heard of lookup tables. Lookup tables are simple hardware primitives that typically take in a few inputs and then output a single bit. They've been around for ages, and overall, they're not super hard to think about because there's already automatic tools within hardware compilers that can reason about lookup tables effectively and synthesize designs onto lookup tables. But as Andrew talked about, there are other types of primitives, more complex primitives like digital signal processors. Digital signal processors have a lot more different types of configuration to do because they can do computations much more effectively if used correctly. As Andrew talked about, oftentimes there's non-optimal usage with digital signal processors, however. One thing that's important to note, though, is that there is still automatic usage of digital signal processors in hardware compilers. Your hardware compiler can still automatically map a high-level design to digital signal processors, if not effectively. This is not true for what I like to call the really wacky primitives. There are some really strange primitives out there, and one example that we're going to talk about today is this thing. It's called a reconfigurable lookup table. And they have several different outputs that you can configure, and sometimes you can configure them to have multiple or only one. They have outputs that go back into itself and change the behavior of the lookup table, and they have outputs that can be chained into other primitives. So it was a pain to even just talk about this. How do hardware compilers look at them? And the answer is that there's actually not any really good automatic compilation for these really tricky primitives. So you might be asking yourself, if there's no automatic compilation and they exist, how do people actually use them? And the answer is quite unfortunate, which is that you must manually instantiate these primitives in your high-level design. Now, if you think about that for a second, that's not so different than having to write inline assembly. Obviously, this is a scenario that nobody wants to live with. I don't even want to look at Verilog. I want to write even less structural Verilog. So I just want to be able to pass in my high-level design into my compiler and then have it do all the work for me effectively. So in the work that I've been doing, I've been trying to work with reconfigurable primitives and get better automatic compilation for them. So in my poster today, I'm going to be talking about the ongoing work that I'm doing to support runtime reconfigurable primitives using sketch-guided synthesis. This is part of a larger project we've been working on called Lacro to broadly cover hardware FPGA compilation. But I'm going to focus on specifically one really tricky primitive called the configurable LUT5 by a company called Xilinx. And I'm going to talk about the initial progress I made with supporting it so far. And I also want to describe some of the future directions with supporting highly complex behavior that I feel we have been limited by the current scope of hardware compilers. And with more advanced techniques of compilation, I believe that we can actually use these, we can actually expose much more potential with these really tricky primitives that is otherwise unseen. So hopefully you come to my poster and we can talk more about it, and hope to see you there.
All right, we're going to wrap it all up with Bhakti. No? Am I? No? Now I'm on. And Bhakti's going to tell us about visualizing graphical proof. Please, take it away.
Okay. Hi, everyone. My name's Bhakti. I'm a student at the University of Chicago. And today I'm going to talk about visualizing graphical proofs in Coq. So what is the problem here? Well, graphical constructs in a proof assistant are kind of hard and really annoying to reason about. Proof assistants like inductive definitions. Graphs do not like inductive definitions. And defining a graph inductively does not end well for anyone. I'm sure some people have experienced this. Also, when you're working with a proof assistant, you kind of have this constantly changing goal state. So the way I usually work with data structures that are like really hard to look at is I will draw them out. If it's a graph, I will draw it out because it's a graph. But because you have something that's changing so often, it really doesn't make sense to draw it out manually. And why do that when you can, have something better? So the question here is, how do we work with inductive graphs in a proof assistant efficiently? And I mean, I think the solution's a bit obvious. I said graph, you imagine a picture, you don't imagine words. And the semantics are the same, you're talking about the same thing. So just draw the picture, just look at the picture and think about it in terms of the picture instead of the words that are really complicated. Okay, I'm gonna backtrack a little here. I did say graph, it's a little too broad. I said graph so I wouldn't have to give a lot of technical details. But I'm gonna narrow the scope to what I actually did, which was a specific graphical language, which is it's called the ZX calculus, and the graphs are called ZX diagrams. And they represent quantum operations, and all you need to know is that it's a graphical language, and it really likes this notion of connectivity, just like kind of a normal graph. The main thing you're focusing on is what nodes are connecting to each other, how they're connected to each other, doesn't really matter. The ZX calculus provides a complete set of diagrammatic rewrite rules for the manipulation of these diagrams. And what is a diagrammatic rewrite rule? Well, it's kind of just, it's a picture, just like everything else is. And like I said this before, saying it again, connectivity is the most important thing. So, and I will say more about this in my poster. But so when we come to verifying this language, you're probably guessing where this is going. You must do it inductively. You have to define it inductively. And you end up putting a lot of information into one singular structure, one term. There's a lot of complicated syntax. It's just horrifying to look at, and no one wants to work with that for extended periods of time, especially if you're verifying an entire calculus. So what's the solution here? Well, you might guess, you might say, draw the picture, and this is where I go, aha, no, because that's not it. Because you need to draw the picture that actually helps you. And there's a lot of background here, which I would be really happy to talk about at my poster. But essentially, we want to draw a picture that contains the information you need to make progress in your proof. You know, you don't want to look at things that you really don't care about. And that's pretty much all I'm going to tell you here. I'm going to leave you with this really scientific diagram, and if it intrigues you, come stop by the poster. Thank you.
All right, thank you. And that concludes the first round of the SRC. And I would like to remind you that after this session in the industrial receptions, that's when the posters will take place. So please do go see the posters and ask the students some questions.